In lesson 5.4, we're going to be talking about multiple angle identities. The ones we're going to focus on are the double angle and power reducing identities. First one are the double angle identities. We have those for sine, cosine, and tangent. If you notice, cosine actually has 3 different double angle identities we can use to rewrite that. Okay, so these are ones you should have in your notes. Make sure you have those recorded so you can use it for the homework. We're also going to be talking about the power reducing identities. Basically, if we have a sine, cosine, or tangent raised to a power, we can use this identity to break it down. Okay, this is often referred to as the half angle identities. Okay, technically it isn't. We would have to rewrite these a little bit to get the half angle identities, but if you look at your identity sheet, they're going to refer to these as the half angle ones. Okay, so just make sure you understand power reducing can also be referred to as the half angle identities. Example 1, we want to prove that the sine of 2u equals 2 times the sine of u times cosine u. Okay, so we're trying to prove one of those double angle identities you just went through. We actually have to use an identity from 5.3, the sine of a sum, to go through this proof. So if we start with the left side, the sine of 2u, we can rewrite that as the sine of u plus u. Okay, reason we would do that, now we have that sine of a sum, so we can rewrite this as the sine of u times the cosine of u plus the cosine of u times the sine of u. Okay, so if we focus and look at this first term and the second term, doesn't matter the order in which you multiply two things, those are the same thing. So we have 2 times the sine of u times the cosine of u. So we had to use the sine of a sum identity from 5.3 to prove and show why that double angle identity works for the sine function. In example 2, we want to prove that cosine to the 4th power of theta minus sine to the 4th power of theta equals cosine 2 theta. So before we get started with this, quickly refresh our memory on a difference of squares. So if I had x squared minus y squared, that would factor into x plus y times x minus y. The difference, subtraction of two things that are squared. Okay? In this problem, we have to be a little creative, but we're going to use that difference of squares property. So the cosine to the 4th power of theta minus the sine to the 4th power of theta can be broken down as a difference of squares. So that will be equal to cosine squared theta plus sine squared theta times cosine squared theta minus sine squared theta. So using that difference of squares property. If we look at that first factor, cosine squared theta plus sine squared theta, you should know by now that that is equal to 1. That's our first Pythagorean identity. So you have 1 times cosine squared theta minus sine squared theta. Now if you look at your double angle identities, cosine squared theta minus sine squared theta is equal to cosine 2 theta. So this simplifies down to cosine 2 theta, which is what we're trying to prove. So use a difference of squares, Pythagorean identity, and then the double angle identity. In example 3, we want to solve the sine of 2x equals cosine x for the interval from 0 to 2 pi. So all the way around the unit circle, we're looking for all the theta values that will make this equation true. So if we start with the sine of 2x equals cosine x, first thing we need to rewrite that left side using a double angle identity. The sine of 2x is equal to 2 times the sine of x times the cosine of x, and that's equal to the cosine of x. Okay, So remember, common strategy, if we're trying to solve an equation, set it equal to 0. So we would have to subtract cosine x to the other side. So we get 2 sine x times cosine x minus cosine x equal to 0. Now we need to think about what do these two terms have in common. They have a cosine x in common, so we can factor that out in front. So cosine x, we're left with 2 sine x minus 1 equal to 0. So our zero product property or zero factor property, we need to set each of these factors equal to 0. So we have the cosine of x equals 0 and 2 sine x minus 1 equals 0. So if we add 1 and divide by 2, we would get sine of x equals 1/2. So now you need to look on your unit circle. We're looking for the values of x where cosine is equal to 0. Cosine is equal to 0 at theta values of pi over 2 and 3 pi over 2. Now we need to find out where our sine values are equal to 1/2. Well, sine is equal to 1/2 at pi over 6 and 5 pi over 6. So these are the four values that if we plugged into that original equation would make that equation true. In example 4, we want to solve the cosine of 2x equals sine x for the interval from 0 to 2 pi again. And this is our last problem we're going to go through. We're going to end on a really nice and complicated one. So if we start with the cosine of 2x equal to sine x. First thing we need to do is use a double angle identity for the cosine of 2x. There's 3 different ones we could choose. In this case, we're going to use the third one. So we can rewrite the cosine of 2x as 1 minus 2 sine squared x equal to sine x. And now we need to get everything to one side of the equation. I want to make it so my squared term is positive, so I'm going to add 2 sine squared x to both sides. And that will leave us with 1 equal to 2 sine squared x plus sine x. Now all we would have to do is subtract 1 to the other side. So we're going to get 0 equals 2 sine squared x plus sine x minus 1. Looking at that, we need to factor this. Okay? And what we can do is think of this as sine of x. We can just let that be y. So essentially the equation we have is 2y squared plus y minus 1. That is what we're trying to solve. That's a quadratic. You've seen that before. So if we can factor this, then we can replace sine of x back in for y once we get it factored. And this is going to factor into 2y minus 1 times y plus 1. Okay, so now once we see how we can factor that, now we're going to substitute back into our equation sine of x in for y. So we have 0 equals 2 sine x minus 1 and sine x plus 1. So now we have our two factors. We're going to do the same thing we've done in the past, set each of these equal to 0. So 2 sine x minus 1 equal to 0 and sine x plus 1 equal to 0. So we're looking for where sine of x is equal to 1/2 and where sine of x is equal to -1. So if we look at where our y values are equal to 1/2, similar to the last problem, we're going to get pi over 6 and 5 pi over 6. And then where sine is equal to -1 is 3 pi over 2. So those will be the 3 theta values that if we plug those back into the original equation, we'll make that statement true.